Thank you, Athir, for the invitation to come here and for the Access Center. I'm honored, and it's been a pleasure to be at KTH this whole week and have a lot of very interesting interactions with people here. This is joint work that I've done with Mihailo Jovanovic of the University of Minnesota and Stacy Patterson, my former postdoc, who's now at Technion, and Partha Mitra, a physicist currently at Cold Spring Harbor Lab, who has alerted us to the connections between this work and some of the statistical mechanics literature. The title is long. I apologize for that, but as I go through the presentation, you will maybe see the relevance of all of these words. I will start very quickly by giving just a one-slide overview. I think in this audience, I don't really need to motivate coordinated and distributed control problems or network problems too much, but I will mention the main issue that I will be addressing, which is the role of network topology when the network size becomes large, and this phenomenon that we call coherence, for lack of a better name. And I will start talking about this phenomenon in the context of consensus, not so much because we are interested in consensus, but because it's really the simplest setting in which this phenomenon appears and can be described. And then I will spend the second half of my talk talking about the phenomenon in vehicular formations, which is actually what led us to this work to begin with. And what I will talk about is apparently present in many other areas, and so I will spend some time connecting this with other fields and give you some thoughts about this. So I think for people in the Access Center, the idea of coordinated and distributed control is very familiar. We were interested in vehicular strings, or platoons as they are called, some time ago. These have many similar features to problems in formation flights. Recently, I became aware of some nice work out of Belgium on the extremely large European telescope. It's a segmented telescope with about roughly 1,000 mirror segments, where the control problem has some similar features to the sort of vehicular string problems we've looked at. The main issue that arises when you're looking at these large networked systems or large networked feedback devices is that the controller architecture, which is normally something you don't worry about too much in lumped systems or in localized systems, becomes really the major issue, becomes sometimes more important than many other issues that we normally worry about. Which sensors should talk to which actuators? How should information be passed? That becomes really almost the dominant design issue in these large systems. And a common and popular mathematical abstraction to deal with these problems has recently been to look at it as dynamical systems on graphs. So this leads to some beautiful interplay between control and dynamical systems on the one hand and graph theory, particularly algebraic graph theory results, and nice connections between the two. And you'll see some of that today. So let me start. Before I do that, let me explain to you in pictures the concept that I want to talk about today. I want to investigate the effect of network topology on the performance of network control systems. And so I'm going to give, this is a set of pictures from an article written by one of my Santa Barbara colleagues, Francesco Bullo. And it sort of shows maybe a cartoon of what a one-dimensional network, controlled network might look like. These are Canadian geese flying in formation. Even though they're flying in 3D, this is in reality a string of vehicles, assuming that each one of them is looking at their immediate neighbors. They're really flying in a string. And if you have watched this on the Discovery Channel, you will see that they sort of meander, and they're not exactly a tight formation. They can follow each other, but they're not exactly a very rigid formation. This is wildebeest. I'm not sure exactly what they're doing, but these are really for inspiration only. And if you've seen at aquariums or on the Discovery Channel fish swimming in formation, just for comparison, these are really swimming in 3D. It's not quite certain how they exchange information, maybe through feeling hydrodynamic forces, maybe vision as well. But they do seem to move in a much tighter formation than these geese do. Okay? So I am not a biologist, and I will not talk about biological system. I'm using these as an inspiration to think about one-dimensional formations, which is the problem that I will speak about later on, which are vehicular platoons on a freeway, for example. That's a problem that's been popular for a while. And I'd like you to think about the two-dimensional and three-dimensional version of that, not as a realistic formation problem, but just simply as an intellectual exercise. I will also look at networks in higher dimensions. Now, these would not be vehicular networks. These would be networks, say, of algorithms on a distributed computation system, and something a little more abstract than that. So the central question I would like to address is, when can such large formations resemble a solid? Think of the solid as a crystal lattice. So for example, for the vehicular formations, I'd like as a performance objective to have them move like a rigid one-dimensional lattice as you go down the freeway. How closely can they resemble such a solid object? If they can't, and if they sort of meander, we will call this sort of behavior disordered, and we'll see a little more precisely what that means. Okay? So as I said, the easiest setting in which to do this is the standard version, or the simplest version of the standard consensus problem. So let me spend a couple of slides to discuss that, even though most of you are probably familiar with this. So consider an arbitrary network described by a connectivity graph. Our work in this started in collaboration with people from computer science, so we thought about distributed load balancing and distributed computation as a motivation. The state of the system is described by in this case, a scalar quantity. K is the node index, and T is time. So for now, I'm doing this in discrete time. The simplest possible distributed averaging algorithm across this network works like this. You have a quantity at node K, which is x sub k. You give a certain fraction of that, let's call that fraction beta, times what you have to your neighbors, and all of your neighbors do the same thing. Okay? So this is the simplest version of the consensus algorithm. There are, of course, much more sophisticated and clever consensus algorithms out there. I want to use the simplest one because the phenomenon I want to describe is most easily described here. So this is a recursion equation, recursion in time, that describes the evolution of each state. And we can write it as a discrete time invariant, in this case, system. And I've lumped all of the dynamics in this matrix A. The structure of A reflects the structure of the network and the graph. And so it's simply x of t plus 1 equals A x of t. This A is derived from the Laplacian of the graph, and so it's very common to think of this process as diffusion on the graph. So similar to diffusion in space, this is diffusion on a discrete space where the connectivity is described by the graph. There are many well-understood and well-studied properties of A. In the simplest version, A is a doubly stochastic matrix. Some rows and columns sum to 1. This gives you many nice properties. In particular, that there is an eigenvector whose entries are all 1. That eigenvector corresponds to an eigenvalue of 1. If you select beta sufficiently small, then all the other eigenvalues are less than or equal to 1. And so in discrete time, you have a certain kind of stability to be investigated through looking at these eigenvalues. So one question you might ask is, starting from any distribution, will the network eventually equilibrate? Will everybody agree on the same value? So as t goes to infinity, does everybody have the same value, which is the average across the network? So there are well-known conditions for this. It will converge. Convergence will occur if the second eigenvalue of A is strictly less than 1. In terms of the graph properties, it translates to the graph being connected. This is an undirected graph, so meaning existence of a path from any node to any other node. In fact, the convergence rate is given by this number. The worst case error will converge geometrically with a rate equal to lambda 2. And there's been a lot of work. Much ink has been spilled on this problem. And I don't mean that in any derogatory way. I think some people have been criticizing the amount of attention this problem has received. But I personally think that this is a very rich problem. And this is a sign that there are many aspects to this problem where each one of us will see one of their favorite aspects in it and works on some aspect of it. So I do regard the amount of attention this problem is receiving as a positive rather than a negative thing. My particular interest in this is the following. As the graph size increases, lambda 2 will get closer to 1. So convergence slows down. If you thought of it as diffusion on a graph, this network increases. So let's say you start with a concentrated state at one node. The time that it takes for that to diffuse will depend on the network size. And then the question would be, how does this scale with the size? And it's obvious that this must depend on how connected the network is and not the topological properties of the graph. So let's do a few examples to get a feel for that effect of increasing the network size. The simplest example to think of is the ring or the one-dimensional lattice. By a lattice, I mean a lattice with boundaries. The ring would be the same graph with the two end nodes connected together. This is quite easy to analyze because the corresponding matrix is toplets in the case of a 1D lattice or circulant in the case of a ring. You can explicitly compute the eigenvalues. Pretty much everything is known about these matrices, their eigenvalues, eigenvectors. You'll see that the spectral gap, as this is called, behaves like 1 over m squared. In discrete time, that means if you ask, how long does it take me to converge to within an epsilon of equilibrium, it takes m squared steps. You can do the same thing for a d-dimensional lattice. I'm showing a two-dimensional network here. Similar kind of analysis can be done. And the same question is answered as follows. It takes, the number of steps it takes is m to the power 2 over d. D being the spatial dimensionality of the network. So think of the network as a lattice embedded in d-dimensional space. So what this tells you is that as the dimension increases, you can sort of visualize that the network gets more connected, and you would expect that convergence time would improve, as indeed it does. It gets better and better. Okay? I would like to point out that this is really the answer to a specific question I asked earlier. How long does it take to converge to within epsilon? So if I use that as a performance measure, that's my answer. I'm going to use other performance measures in a minute. But time to converge is given by this. It doesn't show that there's any dramatic difference, say, between dimension 4 or dimension 5. It just gets better as the dimension increases. So I'm going to now measure performance in a different setting and see that the answers are somewhat different. So let's look at a stochastic setting where people call this consensus with random disturbances. Now each node is subject to stochastic disturbances. One way to think about this is that if this is load balancing in a distributed computation network, these random disturbances would be insertions or deletions of, say, jobs. So a particular job was put to node k. That means that's an insertion. When it's finished, that's a deletion. But what's important for us now is to look at this model where, again, I have the same A matrix given by the Laplacian of the network. But now I have additive random noise, which I assume to be an uncorrelated white process. And the state x now evolves randomly. And here's a little simulation. Because of the eigenvalue at 1, because it's a doubly stochastic matrix, it's restricted to have this eigenvalue at 1, the mean across the network will drift in a random walk. But if the second eigenvalue is strictly less than 1, they will drift together. They will have a finite variance as they drift together, finite variance away from the mean. In fact, you can calculate what this deviation from the mean is, and the steady state limit of this variance can be calculated from the eigenvalues of the A matrix as follows. It involves all of the eigenvalues, of course, except the one eigenvalue at 1, which is indexed here by n equals 1. So this is the sum of a certain reciprocal quantity, which I'll look at in a second, divided by the size of the network. That's the deviation of any one particular node from the network mean. Okay? So you don't have the value of consensus changes is drifting in a random walk, and everybody is never really at it, but persistently wobbling around it. But the variance of that wobble is given by a finite number if lambda 2 is finite. Remember, all of the eigenvalues are less than 1. So there's a nice geometric way of thinking about this quantity. This is really, here I've taken out the 1 over m factor. This is really the reciprocal, the sum of the reciprocals of the distance of the square of the eigenvalue from the unit circle. So typically, one should think of a plot like this. As the size of the network grows, the eigenvalues will tend to accumulate towards the unit circle, from the inside to the unit circle. And this quantity is the sum of those reciprocals of those distances to the unit circle. Okay? So if you zoom in a little bit, see this typical behavior. This is the unit circle right here. It's not just the largest, it's not lambda 2 that goes to 1, but all of them, I mean, a lot of them. Essentially, if you draw a neighborhood around the unit circle, as the network size increases, typically the number of eigenvalues that go into that neighborhood is unbounded. So this sum is definitely growing. And the question really is, at what rate does it grow? And if you want to form quantities like this one dividing by the network size, will these quantities limit to something finite or not? That depends on how these eigenvalues accumulate, and not just how lambda 2 accumulate, but how all of them do. Okay? So let's see what the answer is for the lattice networks that I've just showed you. Again, these sums can be written down analytically. It's a little more hard. It's a little harder to calculate the total sum, but you can do the asymptotics in large M with enough work. So this is the result. The result is that for dimension 1, a ring or a one-dimensional lattice, the variance of this deviation from the mean grows with the network size as m, grows linearly. Okay? So you could, for very large networks, you will be quite far from consensus, and that deviation will be unbounded in the network size. For dimension 2, it grows as log of m, also unbounded, but of course much more gracefully growing than. For dimension 3 and higher, it is actually bounded. So there's sort of a critical connectivity that comes with the three-dimensional lattice and higher, where there's a sufficient connectivity that even when all are disturbed by the stochastic disturbances, they remain within a bounded variance of each other. So this is a very interesting result. It's similar to results that were obtained earlier in the thesis of Prabir Barua with Joao Hispania. They used the resistive network analogy to arrive at a similar result in the context of distributed estimation. This is an interesting enough analogy that I'd like to spend a slide to talk about it, because not a lot of people are aware of this result, which is a beautiful result and somewhat surprising if you haven't seen it before. So if you think about a one-dimensional network of resistors, it's quite easy to calculate the total resistance from one end to the other and how that grows with the size. That's just the resistance times m. They're all in series. Try to do it for a two-dimensional network of resistors, and it's much, much harder. One intuition you can get is as follows. this is now a two-dimensional network, and I'm growing the network and then probing at both ends and looking at the net resistance. So as I'm growing this network, you can observe that I'm getting more parallel paths between those two ends, yet each path is getting longer. So this is sort of typically the way we try to get intuition for these circuit problems. So which way in the limit does it break? Do I get actually, do the addition of more parallel paths win out over the paths getting longer? It turns out that in 2D, it grows as log m, the resistance. Okay? And you cannot do this problem the way I just described, by looking sort of at elementary circuit analysis. Usually, this result is actually from the physics literature. It dates back maybe to the 50s. And it was done by doing approximations of a diffusion kernel in two-dimensional space. Anyway, I'll show you how to do it another way, but, or in a similar way. But it's hard to do using sort of elementary circuit analysis techniques. The surprising result is that in 3D and higher, the net resistance is bounded. This is true whether you have a finite network that you are growing and you're looking at the net resistance, or whether you have an infinite lattice and you put your probes somewhere and you at some distance and you increase the distance. The net resistance is bounded by some constant, which doesn't depend on that distance. Okay? Same in 4D and higher dimensions. So interesting result, seems to have the same scalings as that consensus algorithm. Let me show you how we do the calculation. So actually, what turns out, the more we worked on this, the more we've discovered other links to the literature, which after you discover them, they seem rather obvious. I mentioned the first one and the second one. And then it's also related to the mean first passage time of simple random walks, because the consensus algorithm I showed you is simply, well, some people like to think of it as representing a Markov chain. You can also think of it, another visual picture is that it gives you the evolution gives you the probability of being at any given location when you do a random walk on that lattice. That's exactly what that algorithm gives you. So the common mathematical problem that's solved in order to arrive at this result is you're typically calculating sums. I've now switched to continuous time. So now the sums are 1 over the eigenvalues. Okay? And the eigenvalues are those of the Laplacian. So all of the eigenvalues of the Laplacian play a role. In the limit, as the size goes to infinity, it's the ones that accumulate, in this case, towards the imaginary axis that play a role. Let me skip, for the interest of time, this. We basically do the calculations by reducing everything to a problem on multidimensional discrete tori. Then you use the multidimensional Fourier transform, discrete Fourier transform, to completely characterize the eigenvalues and eigenvectors of the dynamical system, and you calculate the variances or the H2 norms that way. Just one comment. In the end, when you do all of this, you get sums that look like this. 1 over the asymptotics for large network size are always like 1 over the sum of squares of multi-dimensional indices. And the way you calculate the asymptotics is by observing that this is really nothing but an upper and lower Riemann sum bound to this integral. And this integral, which maybe some of you have seen, is the total mass in a ball of radius 1, say, whose density has a singularity at the origin that behaves like 1 over r squared. And if I look at the total mass from integrated over radius 1 to a small gap around the singularity, which is at 1 over n, I see that it's quite easy to see in this integral that in dimensions 3 and higher, this mass is finite. So the total mass, including the singularity, is finite. But in dimensions 2 and 1, it behaves like log n and n in 1D. Okay? So that's really how the asymptotics are done. OK, so what does that imply for vehicular formations? So actually, the main issue I want to point out from all of this is that when I measured performance in the consensus problem in the random setting, and I looked at coherence, this sort of deviation from mean, I get a dramatic difference in the dimensionality dependence, as opposed to measuring the time to consensus. It seemed to be a critical connectivity achieved at dimension 3, where I actually can achieve coherence regardless of the network size. So keep that in mind. Okay, here's the vehicular formation problem. And again, we're looking at fundamental limitations that have to do with the network topology. So I'm going to simplify the platooning problem to be a ridiculously simple version of a problem that has many other complicating features. So the main question in these so-called automated highway systems, when you have platooning to improve the throughput, is which vehicles how should information be transmitted? Which vehicles should talk to which other vehicles in order to perform this control problem in an acceptable, with acceptable performance? And another important question is, how does performance scale with the size of the network? So there are many fundamental limitations. It turns out, I mean, in our opinion, this is a fundamentally difficult problem in the sense that it scales badly with the formation size. So what I'm going to talk about may not be an issue when the formation size is 10, but it may be an issue when the formation size is 100. Okay? Of course, all the results I'm going to present are asymptotic. So then it's an open question as to exactly how bad it is for any given finite network. So some of you may have seen this video. This is from the California Path program. This is a road test done, I believe, in 1997 on a stretch of freeway near San Diego. These are doing fairly good spacing control, traveling at highway speeds. And a lot of nice tests were done back then. What I'd like you to think about is that this is a nice stretch of the freeway. The sun is shining. It's beautiful in San Diego. Imagine the same situation when you have 100, 200 vehicles in this formation traveling on a road that has potholes in a thunderstorm. So lots of disturbances and a large network. Will you expect to see a behavior like this, or will you expect to see something different? Okay? So again, let's look at the simplest version of this problem. My model for a platoon or for a vehicle is laughably simple. It is simply F equals ma. I'm ignoring engine dynamics completely. I have a direct force input into the position of the kth vehicle. That's your, say, the throttle on the kth vehicle. But they're all subject to random forcing disturbances, uncorrelated. Here, it's assumed they're uncorrelated. And these represent, say, wind gusts or pothole forcing and so on. The objective is very simple. Everybody is supposed to travel on a grid that is evenly spaced at some uniform velocity down the freeway. That's what that is. I'm going to use, to describe my states, the deviation of each position from the grid. So the desired state is 0 in all of these. The controls, I'm going to stack all the controls in a vector and assume that the vector of views is given by a state feedback on both the position and velocity deviations. The structure of the K and F matrices will determine who talks to whom. Okay, we'll address that in a minute. The closed loop system looks like this. Here's an example of a certain strategy that is popular and works to some extent. So you can use a simple rule that says the following. The control on the kth vehicle is some number times the slot error, so deviation from delta is the desired spacing, between you and the vehicle in front of you, similarly between you and the vehicle behind you. So that's a look ahead and a look behind policy. And you do the same thing on the velocities. it's quite easy to find numbers, k plus k minus and f's, to guarantee global stability of this formation. Okay? I should point out that if you, usually when people do these problems, one has to make an assumption about what the lead vehicle is doing. It's sort of traveling at a constant speed by itself, unencumbered by disturbances. Sometimes people call that the fictitious lead vehicle. But let's just concentrate on this part of the feedback law. If you simulate what happens to such a formation in the presence of stochastic forcing disturbances, you always will observe a phenomenon like this. So this is an example of what you will see. I've plotted here the trajectories of 100 vehicles. All the trajectories are plotted relative to the vehicle in front. So the vehicle in front is just at 0. And this is the time trajectories. And so this really shows you a kind of motion that looks like this. If you zoom out, if you ride in a helicopter above this formation, what you see is an accordion-like motion, which is a bit slow. You can see that these variations are sort of slow. And sort of the entire formation is undulating. The question now, if you zoom in, what do you see? Well, if you zoom in, for the particular parameters of the simulation I've chosen, there are no collisions. No vehicle runs into the neighboring vehicles. And if you're riding in any one of these vehicles, you will see that the gap is well regulated between you and the next person. You just feel that you're maybe slowing down and speeding up, but you don't know why that's happening. So microscopically, on the small scale behavior looks quite good, but macroscopically it looks quite bad. Okay? And now, of course, the natural question, one more observation. Sometimes when I show this, people say, well, isn't this the so-called string instability that occurs if you design your control law badly? It is not. It is unrelated to string instability. And here's one way to see that. Here's a simulation where the front vehicle is subjected to random disturbances, but the disturbances have been turned off on all of the other vehicles. And you can see an interesting sort of behavior where the temporally high frequency component of the motion seems to be well regulated as you go into the formation, while the temporally slow motions are penetrating fairly deep into the formation. So here I'm going further and further. These are maybe 15, 20 vehicles. And you see the temporally slow motion actually penetrates very far into the formation. That's a signature of those big accordion modes I showed you earlier. So that's an interesting feature, and that seems to be fundamental to these problems. So naturally, the question, so there's no string instability here. If there was a string instability, these perturbations would actually grow as you look down the formation. But they don't. They actually decay. So is this due to my bad design, or is this fundamental to this problem? Of course, you could say, well, maybe you didn't design these gains correctly. Or maybe I should look 2 neighbors ahead and 2 neighbors behind, or maybe 3, right? So we first observed this in what gave us some feeling that maybe this is fundamental to the problem is we first observed this actually in optimal LQR controllers. And this is an old problem formulation that goes back to the 60s. If you do an LQR problem where you penalize velocity deviations, control effort, and you penalize position deviations as follows. You take the slot length error, you add all of them up together, and you make that your part of your state regulation objective. Again, you get a control law that does not have string instability, but has very similar features to what I just showed you. In fact, if you look, we re-examined this recently, and one can see a lot of things about this. One of the important features of this optimal LQR design is that the closed-loop eigenvalues have an interesting behavior. This is a plot of the closed-loop eigenvalues for a formation of size 50. This is the optimal LQR. If you increase the formation size to 500, you will see a very similar plot with just the eigenvalues becoming denser in this these two segments. And in fact, in the limit, one can study the infinite formation limit. The closed loop spectrum actually becomes this continuous spectrum, which is those two line segments. But what's important is that the way the problem had been set up, the point 0, which is not in the closed loop segment, actually attracts these eigenvalues as the number of vehicles goes to infinity. So if you draw a neighborhood around 0, eigenvalues will accumulate towards that. And this actually is a system which has an interesting property, which is that the the closed loop A matrix will be normal. And so you can characterize the energy in the modes in terms of 1 over the distance from the imaginary axis. In fact, this quantity right here actually can be interpreted as the full H2 norm, but also for each separate mode, it's the energy contained in that mode if I do white noise excitation. And so you would expect these modes to be close to 0 to be the most problematic one in the system's response. And if you actually look at those modes at the eigenvectors, which now can be interpreted as spatial modes, they will tend to have long spatial scales. So those are the ones responsible for this accordion-like motion. So this happens in the LQR problem as well. And one interpretation that one can give is sort of a multi-scale effects of feedback as follows. I have a system where the dynamics are local, both because the network dynamics are local and the feedback of the controller feedback is also local. I am feeding it white noise that has all spatial and temporal scales in it. And I observe the response, and I see that in the response, the large-scale modes are not well regulated. But the small-scale modes are well regulated. So you may say, well, this is very natural. If you want it, because your controller dynamics are fine scale spatially. So if you want to regulate against large-scale modes, you need to pass global information around to control large-scale modes. It turns out that that is indeed true in dimension 1, somewhat true in dimension 2, but in higher dimensions, the surprise is that actually local feedback alone will be able to regulate these large-scale modes. So this problem I showed you, this undulating accordion motion, would not exist for a formation of, say, dimension 3, with only local feedback. But for vehicular platoons, which are one-dimensional formations, you cannot get rid of it unless you pass global information around. Okay? So how do we investigate this? Let me very quickly just show you the setting. We do this for multidimensional tori and lattices. Under some assumptions I will show you in a minute. But let me adjust the control law a little bit. This is an example of a local control law based on different measurements of differences. So you can implement this, for example, if you have ranging devices, measure the difference between your position and somebody else's position. There's another kind of feedback which you could implement if you had measurements of absolute values. So this feedback would be x of k, my position, minus where I ought to be on that traveling grid. In order to do that, I need global information. In fact, I need my position relative to an absolute frame of reference. The way this is assumed in the platoons literature is to say that everyone knows their distance to the leader. The leader broadcasts that information. If you think about implementing it, it's a little bit tricky, because in a vehicular formation, that means everybody has GPS, and then the leader communicates with everybody, tells them their GPS position, and then comparing my GPS position to the leader, I know my distance to the leader. Remember, I don't have a ranging device to measure my position to the leader, because that's occluded by many other vehicles. But that begs another question, which is GPS information, are those measurements accurate enough to do control at this time scale? That's still an open question. But let's assume that you're able to measure your position relative to a, say, moving frame of reference, which is so an absolute frame of reference that's moving. I'm assuming the leader is sort of carrying the frame of reference with him, and you can measure relative to that. This last measurement of your velocity relative to an absolute frame of reference is quite easy for a vehicle. That just requires your velocity relative to the desired velocity. If everybody knows the desired velocity, and I have a speedometer, I can measure the difference, right? But if I'm a flying vehicle, that's a much harder problem to do, measure my velocity relative to an absolute frame of reference. So the ones in red are grouped under relative measurements. The ones in blue are absolute measurements. The choice of colors should indicate for you that you can do much better with blue than with red. And we measure performance by looking at this long-range deviation. So this captures the undulating motion. This is the position of the last vehicle minus the position of the first vehicle, or vice versa, sorry, minus what it ought to be, delta times m. The variance of that captures this undulating motion. So I'm going to call this the macroscopic performance index. And we can calculate asymptotically what happens. So here's an example for relative position measurements, but absolute velocity feedback. Then I get scalings like this. At the one-dimensional formation, that macroscopic error grows as m. In 2D, it grows as log m. In 3D, it's bounded. So very much like the consensus problem. So what this means is that with only local feedback, it is impossible to have a one-dimensional formation that behaves like a solid. And these, by the way, are not just they're upper and lower bounds. They're lower bounds under the following conditions. The local feedback laws are assumed to be, by local, I mean I can observe as many neighbors as I pre-specify with a window of size q. That window size remains constant as the formation size goes to infinity. That's what local feedback means. We assume that we have what we call a spatially invariant formation, meaning the masses are equal, et cetera. And the feedback laws are also shift invariant in this context. We don't know if this assumption is absolutely necessary for these results or not. And of course, we assume linear state feedback, okay? Linear static state feedback. So how many of these assumptions can be relaxed is still an open question, but I'll say a couple of things about that in a minute. Here's the full set of results. I would like to just draw your attention to the second column when I talk about the macroscopic disorder, which captures this undulating motion. There's a 1 over W that appears in all of these. W is the control effort. So if I assume bounded control effort, which is a reasonable assumption, then that's where that goes in. The consensus problem I've already talked about. If I have absolute position, absolute velocity feedback, I'm in the best of all worlds, and I can actually obtain coherence. If I have either relative position, absolute velocity, or vice versa, I am in the situation that I just described. So one-dimensional formations cannot be made tight. If instead I have both relative position, relative velocity feedback, so I can't have absolute feedback on either of those two, it gets much worse. In dimension 1, the disorder measure scales as m cubed. And I will need to go have sufficient connectivity that comes with a lattice of 5th dimension in order to actually get coherence to be achieved. Okay? This has to do with the fact that with relative position, relative velocity, I have a problem where each node has 2 states instead of 1, as in the consensus. The disturbance enters into the velocity state, and I'm measuring performance in terms of position. Imagine a worse situation where I have maybe n states. Disturbance enters at the bottom, and I'm measuring performance in terms of the top state. So a chain of integrators of n integrators at each node. Then I would have to go to dimension 2n plus 1 in order to get finite coherence in this case. So the vehicular platoon problem behaves worse than consensus because there's a second-order dynamics at each node. Okay? Here's to give you a little bit of intuition. Here's a one-dimensional formation. This is anchored at one end, and the state actually is a 2-vector in space just to exaggerate the motion, compared to This is 100 units, and this is 1,000 units, 10 rows. And you see these, their connectivity kind of binds them together against the disturbances that are entering everywhere. So this makes you want to think of a fabric analogy. The two-dimensional and three-dimensional meshes reinforce each other. And this actually is almost something that can be made precise. And the reason we actually were sort of driven in this direction is by our physicist friend Partha Mitra, who pointed out to us the connections between these problems, the possible connections between these problems and the problem of harmonic solids. So physicists study harmonic solids as a simple model of atomic lattices, where you have balls and springs. And they ask the question, can short-range interaction lead to long-range order? What that means is that these masses interact with each other via intermolecular forces, say, if you think of them as atoms in a lattice. And those interactions are always short-range. But yet, crystals form. And a crystal is an entity that has basically long-range order. So positions that are very far apart are correlated. And the question is, how can short-range interaction lead to long-range order? This is very parallel to the questions we were asking. Short-range interaction is really synonymous with local feedback. Long-range order is this tightness. It's sort of related, maybe not exactly, but related to this notion of coherence that I was describing. And so in the statistical mechanics literature, this is very well known, that by study, but it's done by studying not these variances I showed you, by studying these long-range correlations. It's shown that in dimension 1 and 2, short-range interactions cannot lead to long-range order, while in dimension 3 and higher, long-range order, in fact, emerges. Okay, so the way the physicists like to say it is that solids can only exist in dimension 3 and higher. If the world was 2 or 1-dimensional, everything would be a fluid or a gas or some other disordered state. So I am told this is not exactly correct. The dimension 2 case is more subtle. There are many possibilities there. One thing to keep in mind is that even though this could be useful as an inspiration, in atomic lattices or in the statistical mechanics literature, n is much larger than the typical sizes that maybe we can think of in terms of formations. But that's problem dependent. I am told that I am probably very much out of time, but let me close with just one thought. The natural question to ask here is what happens for more general graphs? So I've only looked at lattices so far, but they served as a useful model. And the question is, if I have a general graph, what is the corresponding notion of the dimension of that graph? In order to do this, well, it's quite easy to show that you can come up with counterexamples to show it's not node degree, and it's not the diameter of the graph that captures this. So in order to do this, one has to come up with a class of networks that can be grown in size. So there must be some kind of a growing algorithm. So the simplest thing to try, and we've been able to do that, is to look at these fractal type networks. So there are these tree-like fractals that you can generate in a simple way. And you can, and there's something called Vicek fractal, which we also looked at. And there's another one I'll show you in a minute. These have a notion of what's called the Hausdorff dimension. Because for a while, we thought the Hausdorff dimension of the network is really the important quantity. That's sometimes called the doubling dimension of a network, essentially the same thing. So those can come in a variety of Hausdorff dimensions. And we were able to calculate, they have recurrence relations for the eigenvalues. So we were able to calculate the asymptotics of the eigenvalues and calculate what the asymptotics of the coherence quantity will look like. This is to be presented at the upcoming CDC, actually. There's a lot of data in this chart, but I want you to look at the Hausdorff dimension here. So the 1D lattice, of course, has dimension 1. The 2D lattice has dimension 2. And the ones we've chosen here have Hausdorff dimension that lies in between. This is, just look at consensus type first order coherence. This is how it scales for those networks. And you can see that for these Witschek and tree-like fractals, the scaling sort of lies in between n and log n. But this particular fractal network, which has Hausdorff dimension 2, the scaling is like square root of n, not like log of n. So this means that the Hausdorff dimension is not the right concept to generalize this notion. So the right notion is yet to be discovered. It is probably related to the spectral dimension, but the definition of the spectral dimension, which I don't have time to go through, is essentially something like the sum of the tails of the eigenvalues of the Laplacian. So it's really essentially the same thing. What we're trying to find is a quantity that you can calculate from looking at the topography of the network, not something in terms of the eigenvalues, because we know what it is in terms of the eigenvalues. So that remains to be discovered, I guess. I will just maybe stop here because of the lack of time and mention my collaborators. Stacy Patterson was a graduate student in computer science with Amr Al-Abbari at CS when we started doing this work on consensus. And my former student, Mihailo Jovanovic, who actually started this, where he did a chapter in his thesis on formation control and discovered the ill-posedness. And then Partha Mitra, our physicist friend, who pointed out the connections with statistical mechanics literature. So thank you for your attention. I'll be happy to answer any questions.